opportunity to present some of the research work, state of art on foundation, and some of my research work, which I am doing currently and I have done in my PhD. So I'll start with this talk. So just I'm sharing my screen. So can you see my screen, sir? Yes. Yes. Yeah, this is okay. Yeah, so today my talk is actually about the capacity design of foundation, a modern perspective. So it's a completely different thing, which is actually not conventional, like Tarjagi theory and Meyerhof theory and so many bearing capacity theory. So I'll come up with a conventional bearing capacity theory and come up to the capacity design, why it is required and how can we cope up with this capacity design or new concepts. Although it is not that new concept, it is very common in case of offshore foundations, where the foundations are subjected to large shear force and bending moment. And in case of building design and others, there you should not, you don't have this much large amount of shear and bending moment. So usually we ignore in that case. In some cases, I will show you how these capacity design is necessary. You cannot ignore, or you cannot design your foundation with the conventional concepts. So for that, I'll go through a very quick review of typical style of foundations, which is very common based on the shape, like a square foundation, circular foundation. And then if you do two columns together, then it is combined foundation. And for the mat or raft foundation. Similarly, if you are putting the brick masonry wall, so it is load bearing wall kept on street foundation, and a special foundation which is used in offshore. Actually, it is sputcan or bucket foundation. So these are the typical style of foundation. So these all presentation is about the shallow foundation, because pile foundation I cannot combine it with that for the capacity design. It will take another lecture or something like. So in this lecture, actually I covered especially the typical shallow foundation and their capacity design. So what is happening? A typical failure of shallow foundations. You can see that we have three different distinct failure, like general shear failure, local shear failure, and punching shear failure. So these three are very common type of failure, and very old times this is actually going on. So general shear failure is actually, you can see in which category and where it is actually applicable, and local shear failure and punching shear failure. Especially punching shear failure is for very loose kind of sand or loose clay. What is about the ultimate bearing capacity, which is actually conceived by Professor Karl Tarjagi, and he assumed that soil follow the Moore-Coulomb criteria, and it is isotropic and homogeneous, which you can see here in Towson. And he assumed that depth is very low as compared to width, which is roughly equal to 1. And the foundation is perfectly rough and rigid steel foundation. Like inside foundation, there is no bending moment, or it is not actually bending. And the base of the foundation is perfectly rough, so there is no sliding. Okay, and this above the surcharge is actually replaced by the above soil is replaced by the surcharge load, and the vertical compressive load is applied at the center of the foundation. This is important. And he assumed that general shear failure mode assumed and no soil consolidation beneath the foundation. So what is happening? He has found the failure surface consists of three different zones: failure zone, which is called as triangular elastic zone, the radial shear zone, and triangular Rankine zone. And this theory is adopted by several researchers, and finally our IS code 6403 1981 has adopted this theory with some modifications, like in terms of shape factor, in terms of depth factor, or in terms of load inclination factor, and general and local shear failure. And there they have given the bearing capacity factors NC, NQ, and N gamma, which you can see. And these are shape factors and depth factors. So the shape factor, actually it is dependent on the shape of the foundation. If it is strip foundations, because this theory is developed for strip foundation, and it is multiplied to the some shape factor to come up with a solution for square foundation and circular foundation. These are the shape factors. Similarly, when the foundation is subjected to vertical load and moment, so what is happening? This type of problem is solved by eccentric vertical load. What we are doing, the length or the width of the foundation is converted to effective length and effective width of foundation, and then from there bearing capacity equations are used directly. If the foundation is subjected to vertical load and shear force, then this vertical load and shear force is actually replaced by normalized force R with the inclination from the vertical ground. And this inclination is given by this inclination factor, IC and I gamma and IQ. So if the foundation is subjected to all three loads, vertical load, moment, and shear, then this load is actually replaced by eccentric inclined load. Okay, so it is E and alpha, and from there they have introduced in IS 6403 the depth embedment effect and the effect of water. Okay, so these are just for the conventional bearing capacity design, and I will show you in which case these are not applicable, and what is the solution. That's the important, that where it is not applicable, because all of the persons in the design office, we are using this method, this bearing capacity factors and other things for every complicated case. So we are not going for the complicated solutions, which is actually applicable for this interactive load. So what is the assumptions behind these loads? You can see, in case of foundations subjected to seismic loading, Gazistas and Apostolou has given that solution that in case of foundation under seismic load, foundation kept on the surface can slide, can uplift, and there is a slightly bearing capacity failure on one side. So it is not, you can see, it is not coming under any general failure or local failure or punching failure. So it has a different category under seismic load, one-sided failure, and different failure surfaces are there. So what are the structural action on foundation on slopes, especially when the foundation is subjected to these three interactive loads? I'm always saying VHM are interactive load. These are actually acting at a time on a foundation. These are not separated load. So what our code and all over the world code is doing, it is actually separating the effect of V and H and V and M. They are not taking together V, H and M. So that's why you have a eccentric E equal to M by V, and this alpha is equal to tan inverse H by V. So there, one more thing is very important to note, that these eccentricity and the alpha, these actually dependent on the vertical load. You can see it is divided by V in both cases. But when the foundation are kept on slope or on flat ground, like in case of short pier bridge, you can see that here when it is subjected to seismic load, so you have an interactive V, H and M, V, H and M, and the bending, the short pier bridge is actually deflected in single curvature. Whereas if you keep your building on slopes, so again in case of seismic load, you have VHM, and it is actually bending, it is actually deformation is actually double curvature. So here the effective height in case of single pier bridge is total height, you can see. But in case of building, it is actually roughly half of the height of the column. And one more important thing, very important, which actually missing in geotechnical engineering especially, here the moment is calculated by effective height into shear force. Not, so you can see very easily that moment is actually related to shear, not to the vertical load. This is important. So treating it with the vertical load, it is actually in complicated. In some cases, it will apply, but in complicated case, it will never apply. So if you design your foundation with this concept, it will sure fail on slope. I'm telling sure fail on slopes. So measure of the projects, you will see they are always using this kind of methodology, which is given in IS code or any other code, but how to deal this kind of problem. So this is very common concept, capacity envelope of shallow foundation. This concept is very common in case of foundations, offshore foundations, skirted foundation, where the foundations are always subjected to large shear force due to tidal wave and wind wave and bending moment. So how it is look like? So now you understand that if we design our foundation according to the conventional concept in a complicated case, so it will not survive, especially on slope. I'm telling, especially on slope. So what I have to do, what we all have to do to design this kind of foundation, especially a shallow foundation. So what is happening here? This capacity, say it looks like as an axle. It is a 3D concept. Okay. So where the vertical load, horizontal load, and moment, it all are working, acting together. So in case of vertical load, you can see, let's say a vertical load V, where our foundation are designed. So we have designed our foundation for a vertical load, design vertical load, whereas our capacity is V naught, the downfall. Our foundation is designed for V, and the capacity, bearing capacity is V naught. So how much is the factor of safety? It is V by V naught. Okay. When you have a complicated vertical force, horizontal force, and moment, all are working together on a foundation, what is happening? It is a point on a 3D space. Inside this axle, you can say axle or rugby ball, and inside that, if you are applying a purely vertical horizontal load, horizontal load H, so what is the maximum capacity in horizontal direction? It is H naught. So factor safety in horizontal direction is H by H naught, whereas in vertical direction, you can see V0H, it is vertical capacity, the factor safety in vertical direction, V by V naught. Similarly, if you apply a moment, so what is happening? The moment capacity is whatever moment M we are applying, the moment factor safety in moment is M by M naught, and vertical direction, it is V by V naught M. Okay, so it is for pure horizontal load and pure vertical load and pure moment load with vertical load. But if you have all three combined loads acting together, so you can see these all points, this VHM point is showing your vertical load, horizontal load, and moment in a space. And what is your factor safety? It is V naught MH. So here you can see that vertical capacity is higher than when it is vertical, greater than for vertical and shear acting together, and it is much greater than actually the lowest factor safety you will find for when all the forces are acting together. So this is the concept of capacity envelope, which nowadays every code is adopting. I'm telling, every code is adopting. So our IS code is not adopting till date. I don't know why. This concept should be introduced in our IS code, and you can see which codes actually it is giving this kind of information. So Eurocode 1998 Part 5 2004 in Annexure F. Eurocode, I'll tell you small information. Eurocode has different annexure, and in these annexures there are two terms are used. One is normative and other is formative. Informative is just for the information, for the sake of information. You can use, you may use. It is not state of art. But normative is the standard procedure. So even Eurocode is also saying this is may be used an extra F. Okay, what it is saying, this is actually the complicated equation. I will show you how these equations are dealt and how to compare with IS code. This is a capacity equation. I will tell you the very simple column analogy where you are designing your column, how you are checking your safety of the column. That when interaction chart is there, with the vertical load and the moment, and your design force is inside that envelope, you are telling that okay, our column is safe. Similar like SB16 it is given there. Similarly, Eurocode is giving for the foundation. You have this inequality, this equation, expression, and if your design forces are inside this envelope, your foundation is safe for seismic condition. So here, normalized functions n bar, v bar, and m bar, it is actually normalized forces. And NED, VED, and MED is the design forces for which you have designed your foundation. Like NED is the vertical force, VED is the shear force, and MED is a moment force. And here Nmax is the ultimate bearing capacity in case of cohesive soil, in case of cohesionless soil. So you can see V is the width of the foundation. F is the dimensionless soil inertia forces. They are also considering the soil inertia forces, and gamma RD is the model partial factor. And apart from that, you have small A, B, C, D, E, F, so lot of parameter, numerical parameters, which I will show you from where you will get. So from this equation, you have to check your foundation, whether your foundation is stable or not under any complicated forces. So for purely cohesive soil, so first Nmax, you have to define Nmax. So here you can see Nmax actually is main parameter which actually used to normalize all the design forces. So here we have a Nmax which is pi by 2 C by gamma m, and gamma m I will show you where from this which table you can get, and then dimensionless soil inertia force which is F bar, and here the explanation of all the terms. There is acceleration terms also. S is actually missing in IS code. In our IS code, there is no S factor. So this factor even not in IS 1893. So these factors are already available in IS Eurocode 1998 part 1. So from there you have to get the soil factors, which is actually nothing but site amplification factor for different soils. Okay, and the constant applied for this general capacity expression, that shear force should not be, it should be less than equal to 1, and your normal forces is within 0 and 1. Similarly, for purely cohesionless soil, this Nmax is dependent on AV also, vertical force also, vertical seismic component also, and dimensionless soil inertia force is actually F equal to AG by G 10 max. Okay, so these equations are looking complicated. I will show you the example how it is used and where we can use these equations. And this is the actually capacity design of foundation, where you can check your foundation and how much it is safe in this direction. So this is the table for those A, B, C, D different parameters, numerical parameters, and this is the table for gamma RD, this model factor. Next is our NCHRP 651 code 2010, where this code is actually applicable for purely cohesionless soil. So you have a foundation where all 6 components are working, are acting together, where F0, F2, and F3 are all 3 translational forces, and M1, M2, M3 are all moments in different direction. Okay, and you can see similar equations are here also in terms of different combinations of loads, and there are different coefficients A1, A2, A3, B1, B2, and these coefficients can be obtained for the surface foundation as A1 and A2 from this formula. And whereas for embedded foundation, the first one is for surface foundation and for second one is the embedded foundation. These components, that A1, A2, A3, these are obtained from this formula. Okay, so why it is important? So in case of foundation subjected to only vertical and shear forces, so you can see foundation at lower vertical load. Foundation at lower vertical load, actually the foundation will start slide if you have low vertical load. So for you can say that if you want more resistant in sliding, you have to apply more vertical load. Simple friction formula, F equal to mu n. If you want more F, you have to apply more N. But it is not actually always valid for soil, because these Coulomb formula is especially for when your both the objects are rough and rigid. Okay, rigid, not rough, rigid. But in case of foundation on soil, soil is not rigid. It actually bend or it actually deform under the vertical. So that's why this curve, you can see, it is not along the straight line. It is actually moving towards, and finally at maximum vertical bearing capacity, it is actually failing. So your foundation is not actually ultimate. You can see that this is the actual capacity envelope where the foundation is safe or unsafe. This is the actual capacity envelope which if you try to develop for a foundation, it looks like in that format, where moments are actually normalized with the width of the foundation, and your forces in two directions, F1 and F2, are the vertical force and the shear force. Okay, so this is actually the complicated formula, but if you try to develop it in Excel and something, you can get and have a feel. I have some example how to use these things. Next is our ASC 4117, which is actually intended for seismic evaluation and retrofitting of existing building. There is a chapter 8 which is actually telling about the foundation design, non-linear analysis and design of buildings with foundations. So here they are giving three different methods: method 1, 2, and 3. These are applicable for different scenarios. I am telling you one of the example, that the foundation springs, you can see KSH, KSB, and KSR. So the foundation springs can be calculated. These are the elastic springs which can be calculated from these codes recommended in code. And embedment, if the foundation is embedded inside the soil. This is for the surface foundation. If embedment is there, so you have to multiply these embedment factors to come up at the foundation level at different depth H, D. Apart from that, your foundation is not always rectangular. Okay, so we are using generally arbitrary shape of foundation if in any project. So how to come up with the solution for the missing area correction and something like, so these formulas are there. I'll show you all the example how to use that. I'm just going through those recommendation by the different codes which actually we are not even using in our daily practice. So here ASC is giving that axial load deformation curve is bilinear, whereas moment rotation curve is trilinear. And these curves are actually generated from for linear procedure, it is different. For non-linear procedure, it is different. And there they have different performance objective. Now, come up to the point for especially for geotechnical engineering. What is this performance objective or performance level? In case of foundation design, we are always going through two different design process. One is your SLS and second is your ULS. So all the bearing capacity equations and other things are actually targeted to the ULS, that is ultimate limit state, where you are going for ultimate bearing capacity failure or something like that. But in case of serviceability limit state, you have to go for different performance level. So this is actually similar to that performance objective, where you want your foundation should be slightly that immediate occupancy, life safety, or collapse prevention. These three performance levels are there. It is defined in ASC 41 for foundations also. So this is very eye-opening for all of us, that these kind of research are already developed and already standardized in ASC. So we should always, I think, we should use this kind of formulations and in our design practice. So for nonlinear procedure, this IOLSCP is there, and for rectangular and I-shaped foundation, it is there. Okay, so for non-linear procedure, these tables are there from where you can get, and these factors F, B, C, G, D, these factors you can find from here, and you can make your own moment rotation and load deformation curves, and that can be applied directly to the base of the structure. So this is a basic pressure mobilization curve for the sliding. I am giving you now, it is interesting. Till that, we have gone through several recommendations of the code and other things. And I am giving you some example how to use this and what is the importance. So example of one of the nonlinear procedure, ASC, and some more research we have combined that I have taken one building. You can see the plan, elevation and 3D model. And what we have to do, you have a foundation, and equivalent soil springs you will apply at the base of foundation, and you have to apply the rotation hinges, okay, and then you have to apply the shear hinges. So finally your foundation, you can see this, your foundation actually it was like this, and now you have to convert your foundation in this format where you have shear hinges, you have PM2 M3 hinges, which is very common in structural design, but not common in geotechnical engineering or geotechnical design. So you can do the analogy of same structural design here on also in the case of geotechnical or foundation design. So how to come up with this interaction surface? For uniaxial, I'm giving you the formula. Uniaxial MU, you can get it from directly from the vertical load, whereas for biaxial, you have to use this equation. And for interaction, similar to the column interaction, where column is subjected to biaxial moment, directional moment. So MUB, similar equations is there for the checking of column, you can remember. And this exponent is actually there, it is 2, but here it is 1.8. So this is the actually finally the model which you come up with the applying these all formulation. There it is looks like something like rugby ball or football, you can say. And here example that what I covered, it is actually for vertical load and moment. What about shear? So in case of shear, Eurocode is recommending some part. So this example is actually connecting all the codes, especially Eurocode and ASC. So foundation horizontal capacity component, it is actually combination of, you can see that R1, R2 and R3, that R2 and R3, okay. So R1 is the base friction, which you can directly connect with P1 into 10 delta. R2 is a soil passive resistance, which you can directly calculate from Coulomb's formula. This is the Coulomb coefficient passive pressure. And R3 is the side friction, side of that foundation. So this can be excluded in case of drained condition. Okay. So finally, you have to use this basic pressure mobilization curve to normalize. It is actually normalized curve. This you can multiply with the thickness of the foundation and the vertical load, and you will get for your own foundation. And this is the shear interaction. So here also you have a shear forces in both direction. So there is an interaction between shear forces also. So this is VB by VBN. So here you can see to calculate these spring forces, you can use, I have developed one software also. You can use this software to directly get those spring constant. And if you click on OK, so you will directly get that results in Excel. And directly this you can apply in case in at the base of building in SAP software, ETAP software, or whatever StatPro, whatever you are using. These springs are directly applicable there. So if we design our building, so I am taking a typical example of building column number 933. If you design your foundation with the factor of safety 1, 2 and 3, you don't know. I have told you that if you design your foundation with factor of safety considering only vertical load, then you come up with the exact factor of safety. But if you have an interactive load, whatever factor of safety you are targeting, you will not achieve. So this is the problem. I have conducted a parametric study where we have designed a foundation for factor safety 1, 2, and 3. And you can see this solid line is actually for column. So if you design your foundation for 3, factor of safety 3, it is way stronger than your column. If you design your foundation with factor safety 2, in compression, it may fail slightly, but in all case, your foundation, if goes into tension, then it will fail before the column fail. So similarly for column number 949, I have shown 2 examples. And what is the effect? These are the hinges pattern developed in the building, a typical building which I have shown. And you can see there in downside that there is springs and sub hinges are also developed in the foundation. So foundation also fail. So this is important. How? If you use this and use the nonlinear static procedure, especially when you are doing pushover analysis, you have to consider the foundations, because actually if you consider your foundation, you can see clearly that your pushover curves are actually different and it is going lower side. So from this example, it is very clear that we should use foundations, springs and other things while we are conducting nonlinear analysis of buildings and other things. Okay, so now you have remembered that what are the structural axes of the foundation foundations on slopes. Okay, so this is the final solution, that capacity envelope of shallow foundations, which looks like that. But how to develop this? Because in case of foundation on slope, there is no solution exactly in terms of capacity envelope. All over the world, there are no solution available for capacity envelope of foundation on the slopes. So how to develop that? So for that, very common method is there. One is your swipe method and one is your probe method. So I used both swipe and probe method. What is happening there? It is very simple. If you apply forces like vertical force and shear force in a ratio on a vertical on a foundation, and you are coming with the ultimate bearing capacity, so this is called a swipe. And if you are keeping a load constant, like vertical load we are applying, and then we are pushing our foundation in horizontal direction, and then if you are coming with maximum horizontal capacity, this method is actually your swipe probe method. So there are 2 methods, probe and swipe method. I used probe methodology, especially it is very fast. What I have to do, I have to you can remember this sign scheme of horizontal moment and vertical. So vertical, actually I am taking downward, is positive. At a given vertical load V1, you have to apply the moment and horizontal shear force and moment in a ratio in such a way that you get a final capacity of that foundation. So I have applied 32 different fixed ratio, and from there you get a surface in that VM plane, V plane. Again, you apply a next vertical load and again apply your horizontal load and moment in a ratio, and change that ratio such that you cover all the points in that. So similarly for vertical load. So in that way, 32 ratio are used and total 11 vertical loads are used. And then at the angular load, we have simply combined all the points with simply a surface, and you will come up with this generated surface. So it's a complicated method, but in case of foundations, a complex foundation, we all have to generate. I will show you the example where it is very important. If you ignore, you will come up with wrong foundation size and other things. So development of this kind of capacity envelope finite element models, I have developed, I told you I have used 2 different methods. For one is your swipe method, one is your, and other is your probe method. And you can see this last H and M. There both method is actually yield same capacity. This is a typical example for slope of 30 degree. Phi is 44. Psi also we have considered the dilation angle and this. So there are two foundations. One is at the face of slope, and one is at the top of slope. So there you can see this is the normalized parameter. You can see in other codes also they are used normalized parameters. It's like non-dimensional parameters of vertical load, shear force, and moments. So these are combined. These are some factors which we have introduced actually how to normalize this vertical load and shear forces. Yeah. So which is actually what is interesting in that. So now you remember your Eurocode formula, very complicated formula, and your NCHRP formula, it is also very complicated. But if you come up with in HM plane at a vertical load, see, so this V bar actually is 0.5, which means you are targeting a factor safety 2. Okay, so you are targeting a factor safety 2, and in HM plane, you can see that this rectangular shape is actually because of Eurocode. Okay, and the NCHRP is actually above that. This red line is NCHRP, which is somewhat circular. But if you go for actual foundations, it is somewhat ellipse, and it is called as like oblique ellipse, inclined ellipse, you can say. Yeah, inclined ellipse. So the major axis and minor axis is not actually collinear with your usual x and y axis. So it is actually inclined with those axes. Okay. So if you design your foundation with Eurocode and NCHRP, so pure vertical load and pure horizontal load, you can see for pure moment, you always come up with a good solution. Okay, but for pure horizontal and vertical load, you can see the blue line is my study. You can see there is a difference, there is a lag between that. So what is happening? Sometimes we are not actually targeting, or we are applying some kind of factor safety in such a way that our foundation are safe. But actually, if you compare, there are some lagging in actually even the foundation on slopes, on flat ground. But in case of slope, there is again comparison of VH and HM. Here you can see these all lines are quite close. So that's why I told, if you targeting your vertical force and moment and vertical force and shear, then it is very good. But if you have a vertical force along with both horizontal force and moment, there is some discrepancy. I'll show you how it is there. Similar to cohesion-less slope, especially cohesion-less slope I'm targeting. So these all methods which is available in the codes, it is all applicable for the flat ground. So I told there is no method for this kind of capacity envelope on slopes. So this is actually motivated we all to do research in this area. You can see here for cohesion-less slope, where phi is 30 degree and beta is actually the slope angle. If you increase the slope angle, actually the foundation envelope is getting smaller and smaller. You can see this blue line is actually for the study, our method, and this red line is for Eurocode at pure vertical load and moment. These are coinciding with the blue lines, you can see very nicely. But not in case of vertical load and moment in positive direction. Okay, so but if this foundation are kept on top of slope, okay, with you can see these actually envelopes are shifting towards right. So these very clearly these methods given in Eurocode or any other codes are not applicable to foundation on slopes. This capacity method. Similarly, if you go in VM plane or VH plane, again with the beta like slopes with flat ground with 10 degree, 20 degree and 30 degree, for 30 degree you can see the capacity is way smaller. Even if you are keeping the foundation at 1/3, still the foundation is not capable of taking any load in this. It is just as the retained capacity is 10% of the vertical load of the foundation on flat ground. So these methods are not applicable here also. So how actually the capacity envelope looks like? So I have taken two examples, stiff clay and dense sand, both kind of soil we have taken in that. This capacity envelope, you can see how it looks like. For slopes, there is a asymmetric shape is there. You can see compare with your flat ground. On slope, it is somewhat asymmetric and getting and shrink also because capacity on slope is actually lower than the flat. Similarly, for foundation kept on face of slope and on top of slope. Okay, so these are three different things. So how actually these envelopes are looking under vertical load, and what is the effect of different seismic coefficients, horizontal seismic coefficients. And you can see for flat, it is actually changing with the vertical load, where I have targeted 5 vertical loads. It is the fraction of bearing capacity. Like I have targeted the factor of safety 6, factor of safety 3, factor of safety 2, factor of safety 2/3, and factor of safety 5/6. Okay, so these are the different factor safety which we have targeted. You can say in that way and see how it is actually changing in HM plane at a given vertical load. Okay, so if these foundations are kept on flat, these are quite symmetric in H and M plane. But if you keep this foundation on slope, actually it is asymmetric, and you can see the asymmetric shape. Also, the shape and also the locus is shifting towards right. Similarly, if the foundation is kept on face of slope, so similarly, this is the locus is also shifting in right side. And yeah, this is quite complicated right now. So I'm making it very easily. Why it is happening? So this is all because of the let's say failure surface. Tarjaki failure surface you will never find in case of complicated vertical movement and shear. You can see in not in any case we are finding this kind of symmetric failure surface. Okay, so these are the reason behind those the shifting of locus, the bearing capacity reduction, and other things. This is the capacity envelope for 20-degree slope at a vertical load Vmax by 3. Usually we are targeting the factor safety 3 in case of foundations on flat ground or on slope. Here you can see that in case of 20-degree slope, that foundations is actually if is subjected to negative moment and vertical load, the failure surface is completely different if it is targeted to positive moment and vertical load and shear forces. So these failure surfaces are completely opposite in this section. Similarly, for 30-degree slopes, which I'm showing you just for the example. So what is the use of this? I have shown you so many Euro code, and CHRP code, ASC code, and our methodology also. But what is the use of that? Why I am emphasizing that we should use it? Okay, so right now the our one of the code is in the you can say in the draft mode, for which I am also the part of this code committee. I am also the part of that team where we are developing the performance-based design code for structure. Okay, so there is one chapter is also there for the foundation. So if you are targeting a very well-designed structure, so what should be the hierarchy, strength hierarchy of the foundation of the structural component? In that sense, like which component should be much stronger or the order of strength of that component. So obviously, we never found, we never want our foundation should fail prior to any structural component. So the hierarchy of strength of the component of structure should be foundation should be greater than column, and it should be greater than beam and other components. So how to achieve this? This is the actually objective. This objective you cannot achieve with the conventional design. So this you have to use the capacity envelope, because this is very common in structure, but not in common in geotechnical or foundation engineering. So what I have done, I'm showing you one case study where we have designed a building. You can see one building, the plan of this building, and elevation and slope is 20 degree. I'm showing you if these buildings have a foundation, and if you design this foundation according to IS code, according to Euro code, and according to the methodology, which I am showing you again in the next slides, there you will see the discrepancy in the foundation width. Means if you design your foundation with IS code and Euro code, you come up with a very lower width of the foundation. It means you required more width of foundation, and your foundation will fail short in complicated case. I'll show you how. For that, since we don't have any methodology for designing of foundations on slopes, actually on face of slopes, hardly we have 4 or 5 targeted literature only available for foundation design on face of slope. So one of my method is there, where I have developed performed a parametric study for the practical parameters of slopes, where slope is varying from flat to 40 degree, and your cohesion frictional soil, so phi is varying from 5 to 50 degree, and your embedment depth d by b is varying from 0 to 3, and horizontal seismic coefficient is varying from 0 to 0.5 c. And ultimate bearing capacity is given by C and CS plus half gamma B and QS. Here I have combined two factors, the surcharge factor and the unit weight factor in one factor, such that you have less error in your method of superposition. These are some charts, design charts, which I have developed, which you can use in design offices and everywhere for design of foundations on slopes. These charts are actually is in log axis. So reading this chart is quite complicated, although I have developed. So for that, I have developed one software also, which you can get here. Yeah. So this software is based on spreadsheet based, and there you don't need to go for these charts, complicated charts. You simply come up with your foundation parameters, your width, depth, and other soil parameters, and the slope property and horizontal seismic coefficient, and you can get directly your bearing capacity factors and the bearing capacity, ultimate bearing capacity. So these tools is available. You can contact me. I'll give you this. Yeah. So hello. Yeah. So this is the how actually we can use this. If you design your foundation, I have told you, if you design your foundation with IS 6403, and I have designed this foundation for Eurocode 7, because Eurocode 8 is only applicable. If you remember, so Eurocode is 8 is applicable only for purely cohesive soil or cohesionless soil. So it is not applicable for C5 soil. So that's why we have used Eurocode 7, where it is given for C5 soil also. So if you design your foundation, you can see the plan of foundation. So foundation B1 is actually designed. These forces are there. You can see in case of slope, you have with the vertical load, you have very huge high amount of shear force and bending moment also, 164 kilonewton and 229 at B1 level, and B4 level, the shear force and bending moment is lower. So you can understand that shear force and bending moment are well correlated than the vertical force. So normalization of, you can see that inclination factor in terms of vertical force, normalized by vertical force is not that suitable, you can say. So here you can see, if you design your foundation and develop your capacity envelope in, you can see HM plane, these red dot, you can see very easily, these red dots are actually coming out of these two envelope at a defined force. This magenta line is showing the axial force for which we have designed our foundation. Okay, so here it is complicated. Now I'm coming to the 2D space. So there you can see, if you design your foundation with IS 6403, your foundation size is 2.4, and you can see here also this green line. Basically, this green envelope is for column. So column has PM interaction curve. So your PM interaction curve is there, and your design foundation, that is 2.4 meter width, we have moment capacity and shear capacity. So you can see foundation is safe in moment but not safe in shear. This red line and the green line, actually it should coincide at this dotted line, but it is not coinciding. So shear force, your foundation is not capable of the shear force if you design your foundation according to 6403. Similarly, if you design your foundation according 1997, year 97 or Eurocode 7, again it is not able to resist this shear force. If you design your foundation with the software or tool I have given in previous slides, your foundation is actually size is coming 4.6, and it is exactly targeting that shear force. So in case of foundation on slopes, you always have to use this kind of tools, or you have to develop your own capacity envelope of that foundation. But in case of foundation, before foundation, all the codes are quite good compared to 6403. And the foundation size is 1.2, 1.6 for Eurocode, and 2.2 for our IS code. So why? The question is why it is safe for all the codes, or you can say Eurocode and other things, because here you have very low H and M. So which we are always designing our foundations for vertical load, and horizontal and moment forces are actually included in different terms, in terms of load inclination factor or in terms of effective width factor. Okay, so here we have very low horizontal force and moment. That's why for a unknowingly targeted factor safety, these foundations are safe. So I am saying our foundations are not always safe if you use these two or other codes. So you have to always go for especially this capacity envelope concepts. So these are the summary of my talk, this lecture talk, that contrary to symmetric failure mechanism of the strip foundation on flat ground, a distinctly different failure mechanism of the strip foundation placed on slope under different direction of seismic excitation. You can see. So this is no more Tarjagi kind of bearing capacity failure. There are different kind of failure. This is asymmetric failure, where there is symmetric failure. So asymmetric or one-sided failure of foundation on flat ground, even under seismic effect, you can see. And maximum horizontal load capacity. This is very important. Maximum horizontal load capacity is achieved at the vertical load ranging from V max by 3 to, means if you're targeting the factor safety 3 and 2, so in between your foundation has maximum shear capacity. And if you're targeting again similarly, so you have also the maximum moment capacity in that range. Okay, and foundation on slopes can resist higher vertical load if applied in opposite direction of slopes. Two different effect, soil inertia and structure inertia, is actually given by Eurocode 8. It is actually giving, I have told you, F bar, where it is soil inertia effect. And then for flat ground or moderate 20-degree slope, marginal effect of soil inertia. But for steeper slopes, you have to consider the soil inertia forces. Okay, shear capacity of foundation on slopes in positive direction is much higher, and it is not important. In negative direction, actually important. That direction will fail the slope. The effective height of the structure and amount of vertical load govern the actual failure mode. And the most important conclusion is comparison of capacity envelope of foundation and corresponding RC columns indicate that the conventional design foundation, without considering the effect of slope and soil and structural energy on bearing capacity, are expected to fail before using RC column. So these are the most important conclusions. So from there, I'll say that capacity design is now the era where all the codes are targeting this performance-based design. This is actually the state of art which we are using. Thanks. This is a figure I have received this best this research which I have shown you in my PhD. I got award from President of India for best doctoral thesis in IT Turkey recently in 2019. Thank you. So, yeah, yeah. Yes, yes. Buildings, yeah, yeah, yes.
ये देखो मेरे ट्रेनिंग
Any question from any of the participant? बोला मैंने.
Actually, it is quite a new concept. So,
Yeah. I am
initially,
Ravindra from Nashik,
yeah,
and it was a fantastic lecture with so many things, and we were engrossed in all those calculations and all those
yes,
detailings.
yes.
Absolutely, we don't have any queries, but I would like to congratulate you. You have done a very nice work, and you have presented it very effectively. So thank you for
Actually,
that. It was a very in-depth study, and to which actually we have not reached also to that level. To be very
yeah,
frank with you.
yeah. Thank you, thank you.
Thank you very much.
Sir, there is
Actually,
one question.
it is quite common in case of offshore foundations. I will share some literature. One book is there on offshore foundation design. There they have considered pore water pressure and other things, everything. So it's complicated situations that directly there are a lot of equations involved in that. So yeah, obviously, if pore water pressure is there, so there is a chance of liquefaction. So you have to design your foundation considering all those factors also, you can say your liquefaction phenomena. So many things will happen. So you can target that. So there is a book by Randolph and Governick on offshore foundations. It has considered all the effect of pore water pressure and wind load and tidal load, everything. Yeah.
Yes. Can we use Gabion basket installation in retaining walls?
Uh, yeah. What?
So can we use the Gabion basket installation in retaining walls?
Yeah, see. I'll answer mainly the capacity design of questions. So it is not actually in that scope. I'll give you answer whatever can mail me directly. Kindly questions ask me the question from the capacity envelope, especially. Otherwise, it will be a very common discussion forum. So first, you ask the capacity envelope questions from capacity envelope, especially. Yeah,
Sir, I think there are no more questions.
yeah, yeah. No, it is, yeah. I would like to. I would like to add something. Uh, right now, we can escape from this kind of theory, but in coming 5 years, I am sure in coming 5 years, you all have to read this because now our IS code means draft mode is ready. So I'm telling it is under maybe in 6 months it is under circulation. So after that, that IS code will come. So everybody has to use. So it's a like glimpse of that, that how to use capacity design in foundation also. Because now we are shifting to performance based design everywhere. We are targeting a particular performance, not based on your factor of safety and other things, where the displacement is important. How much displacement you want, how much deformation you want, actually. Not the factor of safety, conventional, apply the factor safety on load, some kind of partial factor safety on material and something like that. So this is very important. So in coming future, we all will actually encounter this kind of equations and methodology. So if you have any question, so please write me email to this. I have given you the email ID in chat, and I'll answer uh, all of them, and I'll try. Yeah, sir. Yeah, yeah. Yes, yes, sure. Yes, yes. Yeah, yeah, yeah. I can understand. Yes. Yeah. Thank you. Yeah. Uh, Thank you, sir, and thank you, well, sir, especially, and then NITTR and MNIT also, that they are allowing me to give this presentation and other questions beyond my academic activities. So I really would like to thanks to all the institutes and especially my supervisor and research colleagues who has really helped me to develop this kind of concept in different scenarios. Thank you, sir. Yeah.
Thank you, sir. Thank you so much, sir.
Thank you so much, sir.
Hello, Dr. Dhiraj. Are
Yeah.
you there? This is Dr. Jindal. Just
Yeah.
wanted to know which year did your PhD from NIT Roorkee?
Just 2019, last year.
Acha, 2019.
Yeah.
Okay. So you might be knowing Dr. Neeraj also, I guess, from Earthquake.
Yeah. He is actually my junior. Dr.
Junior
Neeraj.
or senior?
Which you are
Dr.
saying?
Neeraj from Earth.
Yeah.
Dr. Goyal,
Yes.
I know. I'm also a Roorkee alumni. That's why I'm asking. I'm from civil department. I've done
Yeah.
some transportation engineering.
Okay.
Just curious. I didn't know Dheeraj, Dr. Dheeraj well from his name. I knew by his face because I was not a hostler, I was a day scholar. So that's why I
Okay.
could recognize his face and all.
Okay. Yes. Yes.
Yes, I understand that very well. I don't know. He has done a remarkable work, and I wanted to compliment him on the same for the same. Just okay. So that's the thing. Okay. Thanks for the session. It was informative. Good.
Yeah.
Okay.
Mhm. What honest. Much. Mhm.
हाँ जी सर जी सर कैसे हैं सर धीरज सर
बढ़िया तुम कहो
मैं सर जबलपुर इंजीनियरिंग कॉलेज आपसे लास्ट ईयर मिला था जब एसटीपी करने आया था
हाँ याद है
वाई सिंह सर की
हाँ
जी
चलो बढ़िया
और
मिलो
सर
मैं
सर आप कब